in case they've fallen asleep. I'm going to continue talking about resonances. Why am I interested in resonances? Because I'm interested in going towards drip lines, and as you go towards drip lines, more and more of the excited states go into the continuum, and when you go beyond the drip lines, of course, you only see the resonances there. Our method of looking at resonances is, what? Is that better? Okay. Our method of looking at resonances through invariant mass spectroscopy. And this is the device we use to do invariant mass spectroscopy. It's the high resolution array built with a collaboration from our university, Michigan State, Western Michigan University in Indiana and Milan, and we use it largely at Michigan State University. We're interested in light nuclei where the resonances are usually short lifetimes, so a beam might come to a target, the resonance decay in the target, and the fragments come out. Of course, in invariant mass spectroscopy, you've got to measure the momentum of all the particles in the decay of the resonances, and this can be either 2 or more particles. I've shown 3 particles here. And of course, you measure the momentum vector, you go to the center of mass, and from the center of mass you can calculate the kinetic energies of all the particles, and we call that ET, the total decay energy, and I'll show most of my spectra are relative to that. Of course, if you add in the rest masses, all the particles, you get the invariant mass. And if you subtract the ground mass, if you know the ground state mass, then you get the excitation energy. Oops, wrong way. So let's consider one experiment. This was done with a carbon-9 beam, okay? And we identify all the particle types, and we can look at correlations between all the different particle types in terms of all the 2-body combinations, and we see 21 resonances. Then we can say, oh, well, let's consider higher multiplicities, right? Let's look at resonances decay into 3 bodies. So we go through much more combinations, of course, but you go through them all. We got 13, and then you can go to, we get 7 4-body and 1 5-body. So in total, we see 42 resonances in these systems. Okay, some of them are close to our projectile, like carbon-10, carbon-8. So these are simple removal or addition of a particle, but some of them are a long way away, lithium-5, lithium-6 states. So we're looking at a variety of reaction mechanisms producing these resonances. The interesting thing I find is that the relative number of 3-body and higher order resonances that we see also point out that our efficiency for determining these higher order resonances is much lower. So in reality, if you could correct for that, we have actually more than half the resonances we see are these higher order things. I think this is associated with being for these light systems. They tend to fall apart very quickly. Now, most of these resonances are known. We actually, oops, what do I have here? Yeah, only 6 cases where we found previously unknown states. But there's a lot of states that are known that they're missing important information, like the spin, the width, and stuff like that, how they decay, branching ratios. So total, in this case, 14 levels where we provided that information. So that's an example in the, for a proton-rich beam. Okay, here we go. I'll show one example for when we have a neutron-rich beam. Of course, we're not detecting neutrons, so we're missing a lot of resonances here. But we have selectivity of the exit channel, and particularly when you're looking at charged particles decay from neutron-rich systems, you often pick out high T states. And we see lots and lots of high T states with this, we have a beryllium-12 beam. I picked out one case here. So this is an exit channel where we had 2 protons and lithium-9. So it's making boron-11. And you can sort of see a peak here. The statistics aren't good, but okay, the decay energy is about a little over 2 MeV. When you put in the Q value for the decay, this level is actually at 33 MeV. So it's in a region of very high level density. And we only really see it because of this exit channel selectivity. This peak is the double isobaric analog in boron 11. It's an analog of lithium 11, the famous neutron halo state. I think yesterday we had a talk where it was discussed how the first analog of lithium 11, that's in beryllium 11, was found at Riken. So this is the third member of an isospin sextet. Okay, there's 6 members because this is T equals 5 on 2. Okay, now if you look, so we can get the mass of this state. So if you look how the mass of these members of this multiplet change, they increase because you're changing neutrons into protons, and these protons then have a larger Coulomb effect, and so the energy goes up. And if isospin is a good quantum number, this should increase quadratically. And so we can actually fit this with a quadratic and extrapolate up to the mass of oxygen 11. That's the mirror of lithium 11. But the most interesting thing I find is that if we calculate how this should go based on normal nuclei, not like a halo nuclei like lithium 11, then you get this black curve, okay? And as you can see, the energy or the masses is decreasing slower, and that's because you're putting protons into the halo, and in the halo the Coulomb energies are lower. And we've took halo wave functions from Haganino and Sagawa, which was predicted for lithium 11, and you actually calculate what the Coulomb energy is then associated with putting protons in such a halo, and you get this green curve, and it fits quite nicely. So we're seeing this halo structure in these analogs here. So this is a case of basically two proton emitter, and the rest of the talk I'm just going to concentrate on 2 proton emitters, but more on the neutron-rich side, sorry, the proton-rich side. Here we go. So when you have an exit channel with 3 particles, the question is it prompt? Are the 3 particles emitted all in one stage, or is there some series of emissions? So you have, one possibility is a sequential case where you're emitting through some intermediate state, okay? And if the intermediate state is narrow, so long-lived, there can be no interaction between the protons emitted in the 2 steps. So that's a really pure case of sequential emission. There have been 2 ideas proposed for how you would get a prompt emission. One of these is from a paper in 1960, Goldansky, and that is if this intermediate state is energetically inaccessible, then the only way you can get from here to there is emitting 2 protons in a prompt process. Things that look like this, nuclei look like this, are usually heavy nuclei where all the levels are narrow, and we had a discussion yesterday, some lovely data from the optical TPC, where we had data from this iron 45 and the nickel case, where one sees such Goldansky type emitters. For the lighter systems, not all these levels are very narrow, okay? So you get cases where you get wide states. In particular, if you have a case like this where the intermediate state is wide, then it was proposed in 1989, they used a term called democratic decay. Now you have to be careful because democratic decay has been used by other people to mean phase-based decay, but here they meant democratic decay is equality of energy scales. And so if you imagine a case like this, the typical energy of emitting, if it's a sequential decay, the typical energy of emitting the sequential decay was of the same order as the width of the intermediate state, then they proposed that this should be a prompt decay. And basically, if the first proton comes out slowly, and the intermediate state's wide, so the second proton comes out straight after it, then the two protons are going to interact, and you have to really describe this as a three-body decay. So most of the light systems are of this type. The easiest ground state two-proton emitter in the light systems is beryllium-6, and it sort of has both of these qualities. You can see here's the ground state, and the lithium-5 intermediate state is wide, okay? So it has this democratic thing, but actually most of the strength is inaccessible from a single proton decay. So it also has this Goldansky aspect. But notice if you look at the excited state, the 2+, it's no longer a Goldansky, but it's still a democratic decay. Let's see where we're going to go next. So, yeah, I should also mention, both of these things are associated with pairing. So if you want to make a Goldansky case, if you make this system even and this is oddsy, then the pairing energy, if you like, pulls this state up and can make it inaccessible. And similarly, the pairing energy, well, when the state's pulled up, it's also less bound and tends to be wider. So both of these things are usually associated with pairing, and one finds that these two proton emitters are always associated with even Z. So I got this plot here where the black and the red are within the drip lines, and you can see these two nucleon emitters, ground state two nucleon emitters are shown in yellow, and they're all in even Z, and of course, by similar arguments, two neutron emitters will also be even N, okay? So I showed you the beryllium-6. These are the other cases where two proton emission has been seen. We're going to concentrate mainly on this case, the beryllium-6 and the neon-16, because we have very good high statistics data. Notice the carbon-8's quite an interesting case because it'll two-proton decay to beryllium-6, which, as I just said, it was a two-proton decator. So you have a sequential series of three-body decays. It's quite an exotic object. So here are some of the other ones we've seen, and this is just the invariant mass spectrum. So this is the decay energy. So this is oxygen-12. We made it from an O13 beam and knocked out a neutron. And you see the ground state and excited state, and here is sort of the decay scheme, and you can see a large proportion of the intermediate state is accessible, but it's very wide. Here is this carbon-8 I mentioned, so it actually decays into 5 particles, 4 protons and an alpha, but we actually proved through correlations that it decays 2 proton decays to beryllium-6, which then 2 proton decays. And here's the other case I'm going to consider. This is neon-16, 2 protons and an oxygen-14. We see the ground state and an excited state, and again, you see the intermediate state is wide. Okay, maybe I'll give this side they're falling asleep over here, so I'm going to give you guys a chance. So, apart from identifying this, okay. You were falling asleep too, so. Apart from identifying these states, what else can we learn about their decay and their structure? So what we have is the correlations between the momentum of the 3 particles, okay? And of course, there's 3 momentum components for each particle, so that gives us 9 degrees of freedom. But we're not interested in the center of mass motion, okay? So we're going to remove 3 degrees of freedom, that leaves us 6. And of course, the decay energy is fixed, so that's another degree of freedom, so that gives us 5. And if we have some arrangement of the 3 momentum vectors and then we arbitrarily rotate it, that's basically the same, so we're not interested. There's 3 Euler angles to describe that arbitrary rotation. We're not interested in that. So that just leaves us with 2 remaining degrees of freedom to describe the correlations. So unlike 2-body decay, where you have a resonance energy, a resonance width, and spin, in 3-body decay, You also have another piece of information you can have, and that's a two-dimensional distribution describing these correlations. So this two-dimensional distribution is some extra information that we can use to learn about the decay and the structure of the state. And here are some examples. Of course, you get to choose what dimensions you plot against each other. And there are various choices you can make. Two popular choices are in terms of these Jacobi hyperspherical coordinates. And this is some distributions in the Jacobi T. And so here is one. And this axis here, it's EX, where EX here is the relative energy of the two protons divided by the total decay energy. And it's versus, because of this angle, and this is this angle here, okay? And what I've shown you is two experimental distributions for a prompt decay and a sequential decay, okay? So this is the beryllium-6, and this is an excited state in carbon-10. And you can see there's a big difference, okay? It's very easy to pick out prompt and sequential. Sequential has two solutions, okay? In the prompt case, we have a big blob, but there are three regions of suppressed yield, and they're expected. In these regions, for instance, this one of the protons in the core, in this case the core is alpha, have the same relative velocity, and so the Coulomb repulsion pushes them apart. And then this region here, the core and the other proton have the same relative velocity, so the Coulomb repulsion pushes them away. In this region here, you have the PP Coulomb interaction pushing them away. Another way of looking at this, an equivalent way, is in terms of the Jacobi Y hyperspherical coordinates. Okay, all right, good. And oops. This case, we have this EX is just a relative energy between the core and one of the protons, and there's this other angle. And again, you see two solutions, okay? Very simple. Let me just skip some of this. So we measure these things. Can we extract useful information? We work with a theorist, Leonid Grigorenko, and he has a model to calculate these things. And so basically you specify the interactions between the free particles, you solve for the wave function, and you have to match with outgoing wave boundary conditions. And it's quite a successful model. So here's the ground state of beryllium-6, and here are the experimental correlations in the T and the Y system, and here is his predictions, and they match up pretty well. Notice there's a little dip here, and it's also in the prediction. And then here is the first excited state, it's a 2+. Notice the correlations are quite different in this compared to the ground state. But again, his calculations match up quite well. So if we believe this theory is telling us about what's happening in the nucleus, can we learn some nuclear structure information? And here we're going to just look at the wave function that this model predicts. So it's the wave function squared. It's in terms of these Jacobi T, X, and Y coordinates. And what we've done is integrated over the angle between X and Y. So here is X versus Y for beryllium-6. And you see the wave function, when the two protons are close to the core, has two quite separate components. Now, let's consider helium-6, right? So that's just a mirror system. It's just an alpha and two neutrons. And in these calculations, you just turn off the Coulomb energy. And instead of matching to outgoing waves, you just make sure it's a bound state, so you have to make sure the wave function decreases as you go out. And again, you see the same structure. Now, to about 10 or 15 Fermis, they're pretty much exactly the same. So we're seeing isospin symmetry here. So beryllium-6 has the halo wave function that helium-6 has. It has these two solutions which are described in this case as a dineutron, and the cigar-shaped configurations, these are present, the diproton, and again, the cigar. Now notice as you go away larger distances, the separation sort of these two solutions disappears, and in the end we see this big blob that I showed you for the ground state. The other case we looked at is neon 16, where you have a lot of statistics, and here is the, again, these are the experimental T and Y distributions, and here's the theory, and it reproduces it very well, okay? Maybe I won't go into this. There's a big discussion could have about how you take into the long-range three-body Coulomb interaction. It's very difficult, and a lot of effort went into it, and but I think I don't have time. But that's one of the important things you have to do to get these correlations right. Okay. Lastly, we talked about these conditions for prompt decay, right? And this case here, the neon 16, is democratic. So this is the ground state, and this is our intermediate state. It's wide, and the kinetic energy of the first emitted proton, if you think about this as sequential, is small compared to the width. But what happens if we go up to here, the first excited state? Now, if you have a sequential K, the energy of the first proton is much larger. So the first proton can travel much further away before the second proton comes out. So is it now sequential? It doesn't satisfy this democratic condition which was proposed in 1970. So we went to look to see whether we were seeing sequential decay. So here is the experimental correlation function, and let's just concentrate on the Y. And you see, as I pointed out, when you have sequential, you should have two ridges, right? And here's our matrix calculation of a sequential decay through this intermediate state, and you see two ridges. But what do we see? Well, we start to see two ridges here, but they don't extend the full way across, okay? So there's some indication of sequential, but it doesn't look right. Now these angles, where the ridges are present, this is where the two protons, their relative angle is small. So this is a region where you expect to have these, the final state interactions between the protons being strong. And so it's sort of nonsensical. We have these sequential ridges only when we have these final state interactions. Here is the calculation from the three-body model, and it pretty much gets the basic structure right. So can the model tell us what's happening, okay? And this is a somewhat complicated thing, so I don't want to go through all the details. When I showed you the wave function before, the wave function squared, it was in terms of these x and y's. Unfortunately, it's now in terms of rho, this hyperradius, and this angle, but they're related by this. But let me just point out the major features. This red region, especially towards the axis, is where the two protons are within the barrier, okay? And coming out from this red region are three ridges. There's a ridge here, and a ridge here. So this ridge is a mirror of this, so it's basically the same. So this ridge here follows approximately this yellow line labeled 2.5. That's where x is 2.5. So one of the protons stays close to the core while the other proton is moving out. This is what we consider sequential decay, okay? So we see this sequential decay. Okay, I'll just finish up after this. And we also see the other case where the other proton stays near the core, that's down here. But in this region here, this is where x and y are the same. So in this region here, we have the two protons escaping from the core at the same time. So we have these both sequential and prompt processes. Now we expect that the flux going down here will eventually turn around, and the flux coming out of here, they will sort of meet in this region. And so you'll have large interferences from these two decay paths. So the strange signature we're seeing is basically an interference between prompt and sequential decay. So you see that the transition from prompt to sequential is not simple. And we really haven't figured out what region, what are the conditions for pure sequential decay. So we also have another case, but I won't go into it. where we see basically the same. So I've talked about this invariant mass spectroscopy. It's quite powerful. As I showed, we saw a lot of three-body resonances. And I sure hope that I convinced you that these momentum correlations are a very powerful tool for learning about these and nuclear structure effects. And finally, I talked about how we have a very complex transition from sequential prompt to sequential. And here are some of the authors associated with this work. Thank you.
Thank you very much. So we have time for a few questions. Mary, I want to ask you a question. Concerning the GSI, there was some data on neon 15 that they also don't see any sequential decay. You have neon 16.
Neon 15, they saw the ground state, yeah. So the ground state of
can you
neon
comment?
15 and 16 are prompt decay.
Yeah, so they're prompt decay. So, but in your case, you have also some sequential part inside.
No, this is the first excited state where we see the sequential part. The ground state is pure prompt decay.
Also consistent with the other neighbor. Okay. Question, Martin? Next time you sit down.
So maybe this is in your analysis anyway, but just to try and understand, if one was trying to do this at higher energies, one could look at the momentum correlations of the two protons and ask whether you can do something like Embry-Brown twists to understand the size of the emitting source. Can you do that to understand the initial state correlations between the two protons?
Well, I'm not quite sure what you mean. I mean, Hanley-Twain-Frist, you're not interested in the initial structure here. So we have a mixture of some initial structure affecting the correlations and then the diproton correlation as they move out. So it's quite intertwined, I think, and I don't know how you can really separate them.
Bob, if you look carefully at the differences between the helium-6 and the beryllium-6, I guess it's a little subtle because one's unbound, but can you see more of an enhancement of the cigar formation for the beryllium-6 because of Coulomb?
Well, we of course, we didn't measure helium-6, so we just did the theory. It's in the calculation. I guess you'd have to look really closely. Those plots were in log scale, so if you kind of looked a little closer, maybe you could see that. Okay.